Welcome to the third instructional video on various math topics relevant to chemical engineering. We will take a break from vectors and tensors today and talk about ordinary differential equations, specifically those pertinent to reactions engineering and process control. ODEs relevant to fluids and heat and mass transfer will be a separate discussion in part 3b, the follow-up video to this one. So we will work through these three differential equation problems in this video, and then we'll briefly talk about this fourth form here on the right side, which we'll be studying in more depth in the Laplace transform video. I will also briefly mention where you might find these forms of DFQs in your ChemE classes. To skip to each example, please use the timestamps provided in the description below. The most common form of DFQ you will encounter is the separable differential equation. All of the examples we will work through today are of this form. When the equation is not separable, the Laplace transform method is very useful, and this will be the topic of part 4 of this video series. If neither method is usable, you would typically solve the equation numerically or graphically using software. So this is the first form of DFQ that we will be exploring today. Typically, you might see this form in your reactions engineering course pretty early on. This form of equation results if you are studying liquid phase reactions or gas phase reactions that are equimolar, which means the sum of stoichiometric coefficients is equivalent on both the reactants and the products side. N is the reaction order, so like first order reaction, second order reaction. In this video, we will be solving for when n equals 1 and for when n equals 2. Typically, x is defined as the reaction conversion, so how much conversion has occurred. 0 being it's pure reactants, and 1 being no more reactants are there. All of it has been converted. And t is time. That's used for batch processes where the system changes over time, but it can be easily replaced by, this dt term can be replaced by dv or dw, v for volume, w for weight, if you are studying a non-batch process, like plug flow reactor or packed bed reactor respectively. And the derivations for all of this you will do in your reactions class. But since today we are focusing merely on the mathematical solution, we will just use dt in our equation as an example. Finally, this letter A is just a constant. Typically, this constant consists of different parameters, physical or chemical parameters like rate constants, initial concentrations, residence time, and that's all based on this scenario given in the problem statement, but we'll just consider it just this constant that we'll label A. Alright, so let's do the first one where we set n equal to 1, so dx dt equals A times 1 minus x to the first power. So the first problem we encounter is, what is the initial condition or the boundary condition? So typically when it's a function of time, which is the case, it's called an initial condition, while if it's a function of space like x, y, z, then it's called a boundary condition. So here, and here it's a first order differential equation here, and by that I mean I'm not talking about the reaction order. Now I'm talking about mathematically. It's a first derivative, so it's a first order DFQ, and in that case we need one initial condition, and in this case that would be, what is x at time t equals 0? And it could be anything. It could be anything. But if you think about it, if you have like a pure reactant feed, at that point that conversion is 0. So conversion is 0 at time equals 0 is sort of that's the initial condition we'll use. It doesn't necessarily have to be that. If there was like a recycle stream that carried product into the feed, then the conversion at t equals 0 would not be 0, but we'll just use this as our basis. All right, so now let's solve the DFQ. It's separable, so we're going to separate the variables. So we'll put x's onto one side, t's onto the other. So we're going to divide both sides by 1 minus x. So we'll move the 1 minus x over, and then we'll move the dt over onto this side. And then we integrate. So now we come to a decision that we can make. We can apply the initial conditions now by putting it as limits on the integral, or we can wait. We can integrate, tack on a constant of integration, and then solve for that constant. Typically in reactions engineering, we do this former method of tacking it, as putting it as limits on the integral. In fluids and heat and mass transfer, you are more likely to do the latter method of tacking on the constant of integration and solving for that. So here, let's put on the limits. So initially x is 0 at time t equals 0, and then we're going to go from conversion of 0 to conversion just arbitrary x, and then from time t equals 0 to some arbitrary time, and that's how we can get basically when we solve this, we'll be able to get x as a function of t. Okay, so now we integrate. So this right-hand side is fairly easy, at from 0 to t, and that is equal to simply at minus 0, right? So at. Left-hand side is the one that's going to be more involved, but this, if you can recognize that it's simple u substitution, where you set u equal to 1 minus x, and du is therefore equal to negative dx, since the derivative of negative x is negative 1. You substitute that in, so the numerator dx becomes negative du over 1 minus x is just u, and you can recognize that that's just negative natural log of the absolute value of u, which is equal to this recast in terms of x, so 1 minus x. And knowing that by definition conversion is restricted between 0 and 1, 0 being no zero product, 1 being complete conversion of the reactant to product, we can remove the absolute value signs, so that just becomes natural log of 1 minus x. From 0 to x, those are the limits. And you can recognize that that's just 1 minus x minus negative natural log, so make that plus natural log of 1 minus 0. Natural log of 1 is just 0. So that's the left-hand side. So now we equate the left-hand side and the right-hand side, and we get negative natural log of 1 minus x is equal to a t. Now, what are we looking for? What's the final answer here? If you are asked to find x as a function of time, then we want to solve for x, in which case that's just a little bit of rearranging. So basically, we want to, here, I'll rewrite that down here. Negative natural log of 1 minus x is equal to at. To rearrange, I would move the negative sign over, exponentiate both sides, e's and natural log cancel, and we get 1 minus x is equal to e to the minus at, and therefore x is equal to 1 minus e to the minus a t. And that's the answer. Sometimes we're not looking for x as a function of time. Instead, we're looking for time as a function of x. And why would we want that? Well, say we wanted to know how long it takes to get from 0 conversion to 75% conversion. How long does it take for 75% of our product, or for our reactant to be converted? And so for that, you would plug in 0.75 for x and solve for time t. And so for that, we would work with what we have here, is solve for t by moving the a over, and what you get is simply that. Alright, so the second one we're going to do is when n equals to 2. So dx dt equals a times 1 minus x the quantity squared. So the n equals 2, of course, refers to chemically this is a second order reaction, but still mathematically it's just a first order differential equation since it's a first derivative, and that's why we just need one initial condition, and we're just going to use the same condition that at t equals 0 our x is also equal to 0. Same as before. And since this is separable, it's a u substitution. A lot of the process is the same as before. What the difference will be is when we integrate the integral with the u, it's going to be u squared instead of u, and you'll see that. So I'll just go through this process relatively quickly. It's the same as before. And we integral, tack on the limits, 0 to x, 0 to t. This right-hand side becomes at just as before. It's identical to before. Left-hand side, process is the same. Set up the u and the du as 1 minus x. Du is negative dx. So the integral then becomes negative du over u squared. And so this is where the difference lies. I like to write this as negative u to the negative 2 power du. And that therefore then becomes negative u to the negative 1 over negative 1. And so the negatives cancel here, and you're left with u to the negative 1 power, or 1 over u. So recast it by plugging in what u equals, and take that from 0 to x, our limits. So now we have to be a little careful because you might first think that the zero one cancels out, but it doesn't, because when you plug it in, you'll see it's equals 1 over 1 minus x minus 1 over 1 minus 0, and this is not 0, it's 1. So 1 over 1 minus x minus 1. And typically we want to write this in just in one term. So the way we do that is we recognize the fact that 1 is simply 1 minus x over 1 minus x. And then we combine the numerators and we get x over 1 minus x. So that's the left-hand side. So equate the left-hand side, right-hand side, and we get x over 1 minus x equals a t. So easily we can move the a over and we have t as a function of x. But x as a function of t takes a little more effort, but it's just some more rearranging. The way we do that is we move the 1 minus x over, we distribute, so at minus atx, and then move this atx to the other side, so x plus atx equals at. Factor out the x is equal to at, and therefore if we divide the 1 plus at over, we get at over 1 plus at. That's x as a function of time. Alright, so the next one is going to be dx dt is equal to numerator a times 1 minus x. And if we had left it just here, it would be identical to the first problem. But now we're going to divide by this thing in the denominator, 1 plus 3x. And so this form of diffie-Q you'll find for gas phase reactions that are non-equimolar. So the number of moles on the reactant side are different than the product side. And so something like that would introduce something like this in the denominator, and in that case the diffie-Q process is a little more complex, but not really, because it's actually the same as all the other problems we've done. It's separable and it's U substitution. So, and then we'll use the same initial conditions to solve it, and then we'll see what the solution looks like. So like I said, it's separable, so we'll move all the x's to one side, so that becomes 1 plus 3x over 1 minus x dx integral is equal to a dt integral, and then the limits 0 to x, 0 to t. And so this right-hand side is literally identical to the previous two problems. Left-hand side, u substitution. U equals 1 minus x, or you can write that as x equals 1 minus u. That will come in handy. And then du is equal to negative dx. Okay, so let's substitute in this stuff. So 1 plus 3x, x is just 1 minus u over u, times dx, which is negative du. So that's a little messy, so let's clean it up. Let's distribute this 3. So 1 plus 3 minus 3u over u, integral, negative du. Okay, and then still clean it up, so that 4 we can, so yeah, that's 4 minus 3u over u, and this negative I can distribute into the numerator, so I'll do that in the next step. So this can become 3u minus 4 over u du. So the negative I just distributed, this switches the order of the numerator. And now since we have two terms in the numerator, we can split up the integral. So this just becomes the integral of 3u over u du minus integral of 4 over u du. So here, in this one, the u's cancel, and that's a pretty simple integral. So the 3u minus this next one is just 4 natural log of u. And so we're going to recast by plugging in what u is in terms of x. That's 1 minus x minus 4 times natural log of 1 minus x. And now the important step is now we have to take this from 0 to x. So let's do that. Plug in x for x. That's pretty simple, straightforward. And then plug in 0 for x, keeping in mind that we're subtracting the 2. So 3 times 1 minus 0 is just 1, so that's that. Minus 4 times natural log of 1 minus 0, so that's that. That's 0. Natural log of 1 is 0. So it's just this whole first thing in brackets minus 3. So, and then I'll just distribute this, so you get 3 minus 3x minus 4 natural log of 1 minus x minus 3. So the 3 here and the 3 here cancel, and you're left with negative 3x minus 4 natural log of 1 minus x. And again, that's the left-hand side. We equate that to the right-hand side, which was at. So at. And solving this for x is a little bit of a headache, so we're not going to do that. Alright, so that's the relationship then between x and t. And solving for t is actually easy. You just divide by a, but that's how you solve this differential equation. But we're going to discuss one more form of differential equation, and that is a times d dy dt plus y is equal to bx. And this is one of the first forms that you're going to be discussing in process controls, and this is actually, we're not going to go into detail, but this is going to be a segue into our part 4 video of this video series, which is Laplace transforms. And what we're going to show here is, in one case where we can simplify it down, this differential equation basically becomes the first one that we did in this video. In more complex cases, we cannot use the methods that were discussed in this video, and then you would have to resort to Laplace transforms. So basically, what are all these variables here? So a and b are actually just constants. X is a function of time, and y is a function of time. And so this x is usually just called an input. Y is called an output. So for example, if you had a reactor, x could be the feed concentration, y could be the outlet concentration, and maybe there's some change in the feed concentration at some point in time, and we'll just call that point t equals 0. So at t equals, so before we start the stopwatch, it was at some value, say 0, and then boom, it's immediately changed, and it was a step change to a new value of concentration. So here, it's actually not a function of time since it's a constant value. Say it's a constant value of 1. It could be any number, but I'm just saying 1 for simplicity, in which case this form reduces down to a dy dt plus y is equal to b, right? So, and then we can move the y over, so dy dt is equal to b minus y. And what you'll notice is this is separable. It's actually very close to what we had in the first problem. We can move the b minus y over to the left side. We can move the dt and the a over the right side. And well, basically, you'll be able to use U substitution and solve that as normal. Thing is, here, you can solve it without initial conditions and keep a constant of integration in, or you can solve it with initial conditions. Either way, you're able to solve this using the methods discussed previously. Problem comes when, what if x is actually a function of time, like say varied like that, like sinusoidally. Maybe the feed concentration is fluctuating for some reason, and that can be modeled by some sine function, say sine of t. And we want to know, like, how does that have an impact on y of t? So the way we do that is we would use the model equation plus y is equal to b sine of t, and as you'll notice, this is not separable. We can't use the previous methods discussed, and so you would have to use Laplace transforms to solve this. The thing is, you can also apply Laplace transforms to this form above, and it's actually much easier to apply Laplace transforms in general. But the one caveat is, if you use Laplace transforms, you need to have initial conditions specified. Without initial conditions, you can't solve the differential equation. And so we'll talk more about Laplace transforms in part 4 of this video series. This concludes part 3A of various math topics in chemical engineering. The next video, part 3B, will continue our discussion on diffie-Qs relevant to fluids and heat and mass transfer. That video will attempt to summarize various boundary conditions found in these courses. Part 4 will continue our discussion of solving more complex ODEs with the Laplace transform.